Welcome to this video series, Catching Chess Cheaters with Probabilities and Statistics. I'd like to explore various aspects of chess playing under the angle of expected human behavior. The idea is to define potential metrics of chess play and scrutinize them through a data science lens. Let's try to understand the game better and, more importantly, detect potential unfair practices like using chess engines in online play. Each episode will focus on a different element of the game and analyze patterns that might reveal the use of engine assistance. We'll use statistical tools to dissect the games, looking for anomalies or numbers that deviate from expected human play. Can we spot unusual ratios or performances that might mean someone is cheating? This series is intended for everyone passionate about chess and fair play. Chess cheating detection is going to be done through Python coding, of course. I want to create relevant metrics. I want this code to be reproducible. Hopefully we'll analyze player data automatically and save a lot of time, and at the end we'll produce the report card on suspicious activity and get some type of rating. Well, I guess that's the ambition. We'll see if we can do this progressively. Last time we looked at Hikaru Nakamura because it was sort of follow up on Kramnik's declaration or insinuation that Hikaru was cheating because he won 45 games in a row and drew 1 out of 46 games, and according to GM Kramnik, this is impossible or suspicious at least. And now, if you saw the previous video, you see that all the calculations were done, and Hikaru for that one came out with a clean bill. And just to validate the approach, we're going to look at Daniel Naroditsky, because this GM on chess.com is very similar in style with Hikaru. He's rated 31-34 as of the filming of this video, the recording of this video, and Hikaru is rated 33-01 on chess.com for Blitz, so they're very comparable, and he's 9th in the US with 2646 FIDE ELO rating. I took, as I did with Hikaru, I took 2 years of archived rated games from chess.com, so it amounts to about 30,000 games. 16,000 games of those 30,000 were played with less than 200 ELO spread. And this is important to me because if you're going to analyze winning streaks, you need the odds to be in favor of one player or another. And this 200 ELO spread is a critical value for me for now. You know, maybe this will evolve, but for now, if you have a spread of 200 ELO over someone, you have 76% chances of winning that game. So this is why we're only considering games where there's at least 200 spread of ELO rating between the two players. We ignored, of course, King of the Hill, 3-check, daily, and Bughouse games because those affect metrics. When we analyze, for example, move time, this could be affected by daily games and Bughouse and etc. So here you have a chart of 17,762 bullet games in the last 2 years. He's been busy, and 12,151 Blitz games and 39 rapid games. Some of the benchmarks here have to be put in perspective of your opponent because there's such a mix of games here. Don't take those numbers too seriously, but when you do compare them with the opponent, you realize that as of Hikaru, Daniel is also faster than his opponents. On average for Blitz, he's at 3.05 seconds per move, 0.52 for bullet, and for rapid 10.71. He's a bit slower here than his opponents. When he's winning, he's playing with an average move time of 1.51 seconds over 2 years. He's tying at 1.86 and he's losing at 1.57. And his opponents are taking more time to beat him. So those are interesting little numbers. And here, specifically by game type, you see the same type of information. Again, this is just a chart that we're going to keep in mind for later use, but it's fun to benchmark move time with respect to the opponent. Checkmate is also another nice benchmark if you're going to consider that someone is resorting to a chess engine, because engines allow you to see deeper than a normal human player, and you're calculating and considering way more lines than a human could. So during the end game or even in the middle game, you're able to see very deep checkmates. So if for example, I don't know what the exact number is, but I think it's fun to track this number. Let's say you won 50% of your games by checkmate. Well, that would be really suspicious. Hikaru at 4%, and here it's 7% for GM Daniel Naroditsky. And we sampled, of course, 30,000 games. How much time does it take you to earn 50 ELO points? This is just arbitrary, right? It could be 100, 150, 200. But the idea is to also benchmark that down the road and do something with this information, because if you're using a chess engine, potentially this rhythm will change. Over a span of 20, 30 games versus, thousands of games that you have on average. So this is something to look at. 41 minutes and 30 seconds. So he gains 50 ELO points faster than Hikaru. It takes him 27 games to earn 50 ELO points. I think it took Hikaru 29 games. So this is not really important for now, but it's a fun stat. Over 2 years, this 50 ELO point gain occurred 535 times, and the losses of 50 ELO points occurred 565 times. Here's the meat of the analysis. Actually, remember at the beginning we said we're not considering games that are below 200 ELO spread because they could go both ways. So if you're gonna calculate a winning streak, or you're gonna look at somebody's chances of winning, you should be starting around 200 in ELO spread. So those are all the games over 2 years that had at least 200 in ELO spread in favor of one player or the other, and they turned out to be, as expected, 11,000 times 616, and they turned out into a loss or a draw 2,409 times, and the player with more than 200 ELO was supposed to win, right? But 76% chances of winning means you should lose 24% of the time. Well, yeah, sure, but here is where, as when you play as black, your 200 threshold is about here, but here you have 500 elo points for those games over your opponent, in favor of your opponent as black. So of course this is going to bring down that 24%, but don't worry, we'll verify all this. And this is the same here, but playing as white when the elo spread is positive. So this is a breakdown of GM Daniel Naroditsky's games. He was expected to win, and he won in 11,608 games because he had more than 200 elo spread against his opponent. And he had 1,300 unexpected losses, and he had 1,106 unexpected draws. So let's have a look at this in more detail. This is a very, complicated graph at first, but it's very simple to understand. Here are all the games, for example, as black, where Daniel had more than 200 elo spread in advantage over his opponent. So there were 3,829 games as black where this was true, and etc. And we keep going. And for example, here he had a spread as black of 500 or more for 248 games in the last 2 years. So this gives you a 95% chance of winning, but it also gives you a 5% chance of losing. So of course this is something we need to consider if we're going to be looking at suspicious play or suspicious activity, because the elo system is really well done. It's a relative rating that's always adjusted, and those percentages are not there by chance. They're there because they mean something. So this is what the next chart is trying to calculate here. For example, he played 3,861 games as black, where he had an absolute elo spread of 200 in his favor. Since he's got a 76% chance of winning with this spread, he's got a 24% chance of losing. So he should have lost or drew 927 times. And the same for white. He played 3,850 games, so he should have lost or tied 924 times. So I did all this for the entire graph that we saw, and I added up, all the upsets that statistically we should have seen by the mere fact that you have an elo spread over your opponent. So theoretically, draws and losses add up to 2,551. And what we observed previously was 2,409. So that's very close. Of the expected games in favor of Daniel, 14,017 games ended up as expected, and 2,409 games resulted in a draw or losses, so it's about 17%. Here's a box plot of the winning streaks. This is the meat of the subject. This is the system I had analyzed for Hikaru Nakamura following Kramnik's comment. And I'm doing the same analysis here for Daniel Naroditsky, but there's way more games than was the case for Hikaru. So on the left here, on the y-axis, you have the streak length. So here, the upper bound here is 12 games in a row. So if you win more than 12 games in a row, you're an outlier. You're outside here. So you can have a streak. Daniel has a streak around 40, 45, 42, whatever that number is exactly. But there's 169 outliers that are games, winning streaks that are superior to 12. And those account for 3,009 wins. And the mean of a winning streak for Daniel Naroditsky is 5. So 5 wins in a row is something that would be considered average for him. And the median, remember, the median is when you sort all your data and you find a value that splits your data in a lower half and an upper half. So three wins in a row does that. Why? Because a winning streak is winning at least 2. One win is not a winning streak, but 2 wins in a row is a winning streak. So you have a lot of winning streaks that are 2 in a row, 3 in a row. This is essentially what this is saying to you. And this is IQR, this little blue rectangle here represents 50% of all the results. So if we look at the numbers, the total games in the winning streaks are 18,674. The number of winning streaks are 3,995. Of course, this is big because we're also counting 2 wins in a row as a winning streak. And the total games in outlier, this part here, over 12 wins in a row is 3,009. And there's 169 such streaks. Some are at 20, some are at 40, you see what I mean? And the upper bound for determining what is an outlier is 12 wins in a row. So if you win more than 12 times in a row, you're in outlier territory. So if we're gonna analyze the games, we have 3,009 games in 169 outlier winning streaks. Why are we considering outlier winning streaks? Because if you're going to be using an engine and if Kramnik is right, well, then you're cheating for entertainment on YouTube or for various reasons. You're using an engine, and this should reflect on your timing and what, for this particular metric, what best candidate to analyze than what we find in your winning streaks. So let's take those games and let's take the outliers in the winning streaks, actually, because if they're going to be extreme values, well, then surely the timing in those moves, the way you play for those games is going to reflect on some kind of unnatural or inhuman ability. So this is why we pick outliers. This is why we consider games that are we consider wins that are part of more than 12 wins in a row. But we filter out, to be fair, rapid and bullet games. Let's focus on Blitz, because I'm going to be sampling some wins from games that are not part of these outlier to compare how a player plays using a chess engine. You need to compare how he plays when possibly he's not using the chess engine. So you have to pick wins that are not part of these outliers. And of course, if you're gonna be analyzing move timings, well, you have to take out the 1 to 5 second increments per game, because those are given every move you make. You gain some time, so it's going to affect the results. So let's consider only games out of these games that are part of those outlier winning streaks, let's consider games that have 0 increment. And what I did is I sampled Blitz games with 0 increment that are not part of the outliers to have a basis to compare with, to make sure that the player is not cheating. You need to compare normal wins with games that are part of these outliers that Kramnik says are unnatural or impossible or suspicious. We'll look at that in the next video, how we define outliers and why they arise. Here I have 761 games that I picked that are not part of the outlier winning streaks, and we have the 837 outliers wins, and we compared here the variance in move times, and we have a lot of moves. If you add up all the moves for those games, for the outliers you have over 35,000 move, and for the sampled games you have 35,000. So this is basically a distribution plot of all the move times. Roughly you can see that the variance of the move times is around here. In general it's around 15 as a value, and of course if you were a bot or an engine, this curve here would be really compressed. This is what we call the skewed distribution. It's skewed right, it's got a long tail, but if you were an engine, this would tend to be more narrow. But of course what we find suspicious here is that the sampled games seem to be played slower than those games that are in the outlier winning streaks. So let's investigate this, but they're pretty similar. Let's find out statistically how they rate. So here I like graphs. Here I took all the games, and I didn't want to show you the 70,000 moves. I think that would make a very unreadable graph, but still this may be for some people unreadable. But here's what I did. I averaged all the move times in every single game that we're considering, like the 761 sample games and the 837 games, the wins that are part of the outlier streaks. So this is showing you the dispersion or the way the averages oscillate between 0 and 7 seconds, and this is the index of the game. So this is game 801, 802, whatever. So this is a cool graph. I think it's kind of nice. So let's make an assumption here. This is what we do in statistics. We'll consider that the variances in move times found in close to 1,600 chess games, the random games I selected from Daniel Naroditsky's play that are wins but not part of the outliers, and versus the games that are part of an outlier winning streak. Let's assume as a null hypothesis that the variances in the move times are equal, and that there's no significant difference in the variance of move times between the two groups of games. So this is what we're trying to prove. To do this, because we saw that the distribution is skewed right, we'll consider the Levene's test, but we'll use a particular version of it called the Brown-Forsythe test. It's using the median instead of using the average. It's a technical thing, but it's more robust this way. let's see here, try to visualize how this test is working. This is just an oversimplification of the test, of course. I'm not going to reproduce all the mathematics of the test, but look here on Y. You have the variance in move times for all the sampled Blitz games. And here is the median, because that test, the Brown-Forsythe test, is using the median instead of the mean. It's a subtle difference, but we can see here that one absolute deviation away from this median on either side gives you a bit the width of dispersion of all the timings, all the move times. So this is a good visual representation, and this test is trying to establish if that little discrepancy here, you see the median is not exactly at the same location. I put everything on the same scale, but of course there are some values that are higher than 120. You can see here that it's not a perfect fit between the two sets, the games that are sampled from the Blitz wins and the games that are part of the outliers winning streak. So this test, this statistical test, this is here just a visual simplification of what it's trying to do. It's trying to assess if these variances are similar. And the F statistics is 0.1042 and the p-value is 75%. So this is really comparing the variances of group means of absolute deviations from their medians. So it's I guess it's complicated, but what it's saying is that, you know, in terms of statistics, we had a threshold of 5%, and now we found the value for this test of 0.1042, and the chances of that value or more extreme value of being found is 75%. So since our significance level for rejecting the null hypothesis was 0.05 or 5%, we're way above that, and we cannot reject the null hypothesis. So based on the evidence we have, based on the data we have, the p-value associated with that data says that we have to accept the null hypothesis, and the variances of move times in the two groups of games are significantly similar. So next, in the next video, we'll look at what constitutes an outlier. Thank you for your attention.